welcome to my channel. I've made a video on stability today, so I hope you like it. If you have any questions, any doubts, you're free to write in the comments below, and do not forget to share, subscribe and like. So now we're going to talk about stability. Before we start stability, we need to know a few things, few definitions which you must have studied in your physics. So one is adiabatic process. What is adiabatic process? A thermodynamic process where no heat is exchanged between a system and its surrounding. And why do we need to know? So there is something known as adiabatic warming, and there is something known as adiabatic cooling. तो adiabatic process क्या है? It's a process जहाँ पे there is no heat exchange within the system. It is either getting cold or heated, but there is no exchange of heat. That's it. It's in a isolation, right? Insulation. So now we talk about adiabatic warming and adiabatic cooling. So we know that air, when it rises, like you see here, it expands and it cools. We've already done this in the previous chapters. And when it comes down, it compresses and it becomes warm. So when it's going up, it's expanding and it's getting colder, and when it's coming down, it's compressing and it's getting warmer. So this is adiabatic warming and adiabatic cooling. This is what just I explained to you. I'll change the color. Okay. So adiabatic warming, the definition is if a bubble of air descends, it compresses and the temperature increases. That's warming. So when air descends, okay, a bubble of air, consider like a bubble of air like in this diagram also. If it's coming down, it will descend, it compresses, right, and the temperature increases. And similarly, when this bubble of air will rise, it will expands, and temperature goes down. So it becomes colder and colder as you go up. Now, very important terms are DALR and SALR. Now, what are these terms? Okay, so DALR is dry adiabatic lapse rate, whereas SALR is saturated adiabatic lapse rate. Now what does that mean? So when dry air, what is dry air? Where there is no moisture at all. It is without any moisture. It is not saturated at all. It's unsaturated air. So basically when dry air, which is basically unsaturated air, there is no moisture, okay, unsaturated air, is forced to rise, okay, it cools. जब वो ऊपर जाएगी, it will expand and it will cool, and this, when it's cooling at a rate, that is known as adiabatic rate, because it's getting colder. Maybe it was 15 degrees here, now it's gone up, it's become 12 degrees. So it is decreasing, the temperature is decreasing, it's becoming colder, and that is known as dry adiabatic lapse rate. Why dry? Because the air is dry, there is no moisture, and this lapse rate is actually 3 degrees Celsius per 1000 feet. So you have to remember this value. This is very important. Now we talk about saturated adiabatic lapse rate. So what is saturated adiabatic lapse rate? Obviously with the name only you can say that it's saturated air. So basically when saturated, or a little bit of, even if there is little moisture, it doesn't matter how saturated it is. It could be saturated. It's not dry basically. So when saturated, that means not dry. So there is moisture present, okay, is forced to rise now. Again it will also cool, okay. Now this cooling is now saturated adiabatic lapse rate. Now this lapse rate is, so maybe it was 15 degrees and now after rising it's become 14 degrees. Why the lapse rate is less? Because there is moisture, and like we know that air will cool faster as compared to water vapor, right? So water vapor takes a little more time to get colder. So the lapse rate is less as compared to this one. So here the lapse rate is, I'll write it in another color. It is 1.5 degrees Celsius per 1000 feet. Okay, this is some fixed values. Of course, in real life, things can be up and down. We'll talk about it. So now what you need to know, what is dry adiabatic lapse rate and what is saturated. Dry is dry air, unsaturated air is going up and it's getting colder at this lapse rate, and saturated basically something that is not dry and is going up and again it's cooling but at a different rate. So these are the two lapse rate. Okay, now there is another definition which is environmental, ELR. So this is environmental, I'll just write environmental lapse rate. Okay, now what is this? This is the real lapse rate that is in the environment. Okay, in ISA we know, as we know that in international standard atmosphere it is considered as 1.98 degrees Celsius per 1000 feet, but in real life it could be anything. So it is the real lapse rate. Okay, we'll consider it at that so that we understand better. This is as per ISA, but this is what is happening in the environment on a particular day. Now we need to know when the situation would be stable and when will it not be stable. So that is very important, and that is on which the questions would also come. Now let's consider this square as this rectangular box as a part of atmosphere so that it's easier for us to understand. Okay, so we need to see when is this condition stable, when is it not stable, and when is it neutral. So first let's understand stability. So now the environment, this is the environmental air, like ELR would be considered as environmental lapse rate. Okay, now let's consider a bubble of dry air here. Okay, this is dry air bubble. Okay, now this bubble will rise at a dry air lapse rate, that is dry adiabatic lapse rate. What is it? 3 degrees per 1000 feet. Now if my air is, so one thing to understand before we understand this is that when the air is warmer than the surrounding environment. Okay, so first part is when the air is warmer, it's warmer than its surrounding environment is less dense and rises. तो इफ माई एनवायरमेंट मेरा कोल्ड है और मेरी जो एयर है, जो पार्सल ऑफ एयर और अ बबल ऑफ एयर वो गर्म है, सो इट्स गोइंग टू बी वार्म, देन इट्स गोइंग टू राइज एंड गेट कोल्डर, राइट? सो इट विल राइज, द वार्म एयर ऑलवेज राइजेस, द कोल्ड एयर ऑलवेज sinks. So when my air is warmer as compared to the environment, that bubble or that parcel of air will rise. So when it's rising, it is creating a unstable condition because there is a movement in air. So this causes instability. Okay. Now the second is when the air is colder than the environment. When the air is colder than the environment, okay, in that case it will sink. It will not rise. It will stay there or sink. So this causes stability. There is not much movement. So it will be there. There won't be any winds. There won't be any turbulence. So it will be stable. So very important. So when the air is warmer than the environment, it will rise. That causes instability. When the air is colder than the environment, it will sink. It causes stability. Now using this concept, let's understand this diagram. Okay. So in the environment, if my air is dry, so now what will happen? The lapse rate is 3 degrees per 1000 feet, and maybe my environmental lapse rate is only 1 degree that day per Celsius per 1000 feet. Okay, because environmental lapse rate can be anything as per the day. So when my dry adiabatic lapse rate DLR is more than my ELR, so let's consider these two conditions. Okay, so जब मेरा dry adiabatic lapse rate is more, मतलब my air is getting colder faster as compared to the environment. So this bubble of air, when it's rising, this air might also be rising and getting colder, but this bubble of air is getting colder faster. So when the air is colder than the environment, it will sink and the condition would be stable. So when my DLR is more than ELR, in that case it would be considered as absolute, stability condition. Okay, now let's consider a same box for, now this is the environmental air. Now let's consider a bubble which is saturated air, any kind of moisture that is present. Okay, now this would be 1.5 degrees Celsius per 1000 feet. Okay, that is your SALR, lapse rate of a saturated air. And let's consider this as 1 degree Celsius per thousand, like we considered it before. That is your environmental lapse rate. Now as compared to the environment, again this air will become colder faster because uska lapse rate ज़्यादा है. ये 10 से it will reach 8.5 degrees, and the environment, if this is my SALR, is 1.5 degrees, you know. So and in the environment ELR from 10 it will only reach to 9. So this would be colder, the temperature is less. Again this would want to sink because it's colder as compared to the environment. So when my SALR is more than ELR, again the situation would be stable. So what do we infer from these two conditions here? That when my DALR is more than SALR, which is a normal condition because dry air will always get colder faster as compared to the air that has moisture, and SALR is more than ELR. In that case, in this condition is considered as absolute stability. So this is very, very important. Okay, I've just explained because this will get colder faster, it will sink when I compare this with this. Again, when I compare this with this will get colder faster. If my SLR is more than ELR, it will get colder, it will sink. So in both the cases it will be stable. So this is known as absolute stability condition. अब हम कंसिडर करेंगे instability की condition. Okay, so let's again take a box only to understand it better within a box. So now let's say कि जो हमारा dry air है, DALR जो है उसका lapse rate जो है वो कम है ELR से. So basically our environment is getting colder faster as compared to DLR. Okay, so this is your environment. Okay, okay, now this is getting colder faster. Maybe this has a 4 degrees Celsius per 1000 feet today. Okay, this is the lapse rate, and this has DALR, this is your dry air. Okay, and this is 3 degrees Celsius per 1000 feet. Okay, now in this case what will happen, this outside air will get colder faster and it will sink. But as compared to the environment, this air will always be warmer, so it will keep rising. Now, because the warm air rises and then it expands and all of that, so as compared, relative air, all these terms are relative, okay? So in this particular time, when this is happening, what will happen? It is going to be unstable. Because it's rising, it's not sinking. So we have to understand what this bubble of air is basically doing. Similarly, so this would be unstable. Now, this is unstable. Great. Now what happens if again SALR is also less than ELR on that particular day? The same condition if you apply. So this, in this case again, this would be colder, the environment air would be colder, it will sink, and this will keep rising because it will be relatively warmer. So this would be a condition of absolute instability. When your ELR, so I'll write it in red because this is another, ELR is more than DALR. DALR will always be more than SALR. Okay, so that's not a point. So ये वाला जो condition है, SALR is less than, it's satisfying, and these conditions are also satisfying. So this is known as absolute instability, because the air parcel will always be rising, it will never sink. Okay, now the last part of this topic is conditional instability. Okay, so in this again we'll take a box of atmosphere where we'll put a bubble of air. Okay, now conditional instability would mean that half is okay and half is not. Okay, so let's take this as dry air again. Okay, the dry air, so DALR जो lapse rate है dry air का, which is more than ELR. That means this environment में this bubble is going to sink and stabilize. Okay, because it will get colder faster because उसका lapse rate ज़्यादा है. So this is conditional stability also, right? So this could be also considered as conditional stability. This is stable. I'll just write stable for now. Now in the on the same day, maybe our ELR is more than SALR. That means that if I take another box of atmosphere and I put a bubble of saturated air and today my saturated air, the lapse rate is maybe, um, would I would say maybe like 1.5 degree Celsius, and my environment lapse rate on the outside is 2 degrees Celsius. So it's becoming colder faster. Now this condition would be unstable, right? Because this air will always be warmer, this saturated air, and it will keep rising within the environment. So it will keep that instability. So when I combine these two, 1 and 2, that means my DALR is more than ELR, that is my stability. But ELR is more than SLR, that is instability. So this is known as conditional, because half is stable, half is not. Conditional instability. So this is taken from IC Joshi. You could just take a screenshot and see it how it works. It's a very simple graph that I've just explained to you. And then these are the questions again from IC Joshi. Very simple, very direct. You just need to understand when it is stable, when it is unstable. The values are changed because in real time everything could be different. So just follow these questions and you're good to go for your stability chapter. Thank you for watching my video. I hope you learned something today, and I request you to please subscribe, like, and share. I'm putting in a lot of effort to make all these videos for you guys. Thank you.